A lot of the features that we're going to look at as we look at symmetry in molecules involve the operation of matrices and the properties of matrices. So I want to spend a little bit of time talking a little bit about how matrices multiply one another and how one can use that to gain a little bit deeper understanding as to what's going on in the group theory. This will largely be a review, largely a math review, so if you are very familiar with matrix multiplication, you probably don't need this video. However, if you'd like to see a little bit of a refresher course on how to think about it, stay with me. Okay, so what I want to do is consider what happens when we multiply two matrices. So I'm going to draw matrices as basically being separated by these curved braces. And I'll say, for example, that I'm going to have two matrices like this that are going to multiply one another. Now, the result of multiplying matrices is, generally speaking, going to be another matrix. So what can we tell in advance about this process? Well, first of all, let me give you some restrictions on it. So let's suppose that we have an array of numbers filling this matrix, and that array consists of A rows and B columns. All right, so this would be an A cross B matrix. That's the dimensionality of the matrix. That's how many elements it would have. All right, next to it, I'm going to have a matrix that has C rows and D columns. So this will be a C times D matrix. Now, can I have any values here and here that I want? As it turns out, I cannot. This only works, we can only multiply these if B and C are the same number. So in other words, these two have to be equal. All right, the resulting matrix that I'm going to get out of this is going to be an array of numbers that has the dimensionality of A times D. So in other words, A rows and D columns. And we'll see why this is in just a moment. It has to do with the mechanics of how we actually perform a matrix multiplication. So let's do this. All right, what I'm going to do just to illustrate this is I'm going to show you the multiplication of a 3 by 3 matrix, and I'll just make some numbers up here. Doesn't matter what we use, so there's no ulterior motive in these numbers, in case you were wondering. And I'm going to multiply by a 3 by 1 matrix. Okay, that seems awfully thin for a matrix, but I'm again thinking ahead to something we're going to need to demonstrate. So this is a 3 by 3. This is a 3 by 1, and you'll notice that these numbers are the same, and they're the ones that we lose in this, so we will get a 3 by 1 result. All right, but how do we go about getting that result? All right, well, the way we do it operationally is I'm going to repeat this matrix over here on the right, but I'm going to leave a little bit of space. So I have 2, 1, 0, and I'm going to leave a little bit of space. I'm going to have 1, 3, minus 2, and I'm going to leave a little space. I'm going to have 0, minus 1, and 1. Okay, now implicitly in here is I'm going to include numbers that I multiply each of these by. And then they're going to be combined, so I'm going to have plus signs here. Since this is a minus, I'll just make that a minus, a plus, and a plus. All right, so all I've done is I've taken this matrix and rewritten it over here, but I've spaced it out. And now I've effectively combined things. So these are the things that will create the first row of this new matrix. And these are the things that will create the second row. And these are the things that will create the third row. Now, in this case, it's particularly simple because I'm going to end up with a 3 by 1. I only have one column in my resulting matrix. So it will be a little bit more complicated if I had more than one column. I would then have this set of operations for each of the columns. All right, but now what do I fill in these parentheses? Well, in fact, what I do is I take the elements of the matrix that I'm multiplying here, and I take this element and I put it in there. In fact, I'm going to put it in each of these 3 boxes. I'm going to take this element and put it in there. So I'm going to go in each of these boxes. I'm going to take this element and put it in each of these boxes. So you can see I'm multiplying these matrices in sort of a convoluted way. I'm taking this set of elements and multiply them by these elements in order. So 2 times 1 plus 1 times 0 plus 0 times 2. 2 times 1 plus 1 times 0 plus 0 times 2. So then when I evaluate all of this, I'll get 2 plus 0 plus 0, or 2. Down here I'll get 1 plus 0 minus 2, so negative 1. And here I'll get 0 minus 0 plus 2. So the result of my multiplication of these 2 matrices is this new 3 by 1 matrix, which is their product. Okay, now why would I choose this sort of strange sized matrix and matrices to demonstrate this? Well, in effect, what I'm doing is I'm mimicking what happens in a 3-dimensional space. So you can imagine that I have, say, an x, y, and z position in coordinate space, and if I array these vertically, as I've done a couple of times in the past in earlier videos, then I can imagine taking some 3 by 3 matrix. So this is a 3 by 3 matrix now that I'm going to multiply by that vector, and the result will be some new vector. All right, so why would that be extraordinary? What we're talking about here is we're taking one vector and converting it into another. So this is a transformation of a vector. And you'll notice that the way to transform it was through the use of a 3 by 3 matrix. Now I haven't said anything about what this 3 by 3 matrix is made up of, just that it be 3 by 3. Why does it have to be 3 by 3? Well, I'm converting a 3 by 1 entity into a 3 by 1 entity. And the only way that I can do this is if I have some number. I have to have this number at the front end, and I have to have the same number here so that these can match up. So I have to have a 3 by 3 matrix here in order to accomplish this. So in other words, this is a matrix way of saying if I want to transform a vector into some other vector, I need to multiply it by a 3 by 3 matrix. Now, this is exactly what symmetry operations are doing. They are taking a vector, and by virtue of a reflection or a rotation or an inversion, they are taking a vector and moving it to a new location, a new spot. They're transforming that vector. So in effect, that means that I can take all of these symmetry operations and express them somehow as a 3 by 3 matrix. Now, there's another way we can write this, and I want to introduce you to this notation, and that is I can write a matrix, and I sometimes will do this with a couple of tildes underneath it. You should read this as representing a matrix. So, for example, this would be a matrix. I'm going to multiply it by a vector, and I'll just put 1 tilde under the vector. The 1 is just basically telling me I've got a one-dimensional entity here. That is to say, one column that I was going to put in there. And this might represent, for example, the following. I might have a matrix that has a whole series of elements, and I'm using these numbers to indicate the row and column number. So this is row 2, column 1, row 3, column 1, row 1, column 2, row 3, column 2, row 1, column 3, row 2, column 3. All right, so these are the elements that make up this matrix. And then I would be multiplying this by some x, y, and z set of positional coordinates to get a new set of positional coordinates, and I'll just mark those with a prime. All right, so this is a sort of notation that we're going to use to talk about matrix vector operations, but I'm going to use matrices that now represent symmetry operations so that we can get a little bit more of a handle on what's happening with these point groups. Now, I do want to point out there's a couple of special matrices, and I'm going to write it up here in the upper right-hand corner. There's a matrix that sometimes is written as a 1, it's a fancy-looking 1, or as an I that stands for the identity matrix. And this can be a matrix of any dimension, but it will always be square. And this matrix will always have 1s along the diagonal and always have 0s everywhere else. So all of this are 0s, and all of this are 0s. And the feature of this particular matrix is no matter what you multiply it by, you will get the same thing back. That is to say, this is like multiplying by 1. So we'll see this identity matrix a lot. And by the way, it is exactly what you get when you invert a matrix. So for example, if I could find the right matrix so that I could find this product, it would always equal this identity matrix. So whenever you find this, it is the inverse of the original matrix A, but you have to be able to multiply them together to get the identity matrix. So we'll see some instances of this in what follows.